Ladies and gentlemen, this is the third lecture in the module of Lean Six Sigma, Measure Phase. During the lecture, the following topics will be covered: Input-Output, XY, Analysis, Pareto Analysis. The goal from Input-Output, XY, analysis is to find X's, process and input measures, that are leading indicators of the critical output, Y. That means, the X's will give an early warning about potential problems with a Y. Such X's are also key to finding root causes, the focus of the analyze phase, and to catching problems before they become serious, and appears on the control phase. So, we can achieve the benefit of early warning. Generally, data is collected on output measures at the start of the project to establish baselines. Use your SIPIC diagram and sub-process maps to help achieve a balance of both input and output measures. The inputs represent the flow of data and materials into the process from the outside. The processing step includes all tasks required to effect a transformation of the inputs. The processing steps include different data depending on process tasks. The outputs are the data and materials flowing out of the transformation process. Examples of the input data are arrival time, accuracy, cost, and key specifications. Example of the process data are time per task, in-process error, labor hours, and exceptions. Examples of output data are customer satisfaction, total defects, lead time, cost, and profit. Lagging indicators are typically output-oriented, easy to measure, because they are results measure, but they are hard to improve or influence. While leading indicators are typically input-oriented, hard to measure because they are predictor measure, but they are easy to influence. The output is easy to measure. You either solve your incidents in 48 hours or not. But how do you influence the outcome? What are the activities you must undertake to achieve the desired outcome? Leading indicators are important for building a broad understanding of performance, because they provide information on likely future outcomes. But they aren't perfect. For one thing, they aren't always accurate. Lagging indicators tell you about what has already happened. However, the obvious downside of backward-looking indicators is they may provide insights too late to do anything about it. The purpose of measuring performance through indicators is to really understand performance and identify ways to improve performance in future. To do this properly, you need both types of indicators. Let us check the following examples for input-output, XY, analysis. Consider Y to be part quality expressed by a dimension measured in millimeter. In this case, the inputs, independent variables X's, are as follows: input material length, material density, tooling, and process speed. But if we consider Y to be part cycle time in minute, then the inputs, independent variables X's, are as follows: process pressure, process temperature, material flow rate, and process speed. For every input, there are an upper specification limit, USL, and lower specification limit, LSL, and target. Now, we will perform an exercise from auto spare part manufacturing facility. The output, or the dependent variable, is the production efficiency, with USL of 95% and LSL of 75% and target of 85%. We need to know the inputs, or factors independent variables. Please pause the lecture and solve the exercise. The input factors are process quality, with USL of 100% and LSL of 90% and target of 95%. Process performance, with USL of 95% and LSL of 85% and target of 90%. And finally, process availability, with USL of 90% and LSL of 75% and target of 85%. For centrifugal pumps assembly department in a factory. The output or the dependent variable is the pump efficiency, with USL of 95% and LSL of 75% and target of 85%. For such output, we need to know the inputs, or factors independent variables. Please pause the lecture and solve the exercise. The input factors are pump capacity gallon per minute, with USL of 930 and LSL of 870 and target of 900. Pump operating speed, in RPM, with USL of 3,620 and LSL of 2,590 and target of 3,600. Head feet, with USL of 192 and LSL of 188 and target of 190. Please perform the activity and send your output by email for assessment. Pareto charts are a type of bar chart, in which the horizontal axis represents categories, rather than a continuous scale. The categories are often defects, errors, or sources of defects, or causes of errors. The height of the bars can represent a count, or percent of errors or defects, or their impact in terms of delays, rework or cost, etc. By arranging the bars from largest to smallest, a Pareto chart can help you determine which categories will yield the biggest gains if addressed, and which are only minor contributors to the problem. Example of a Pareto chart. Bar chart, arranged in descending order of height from left to right. Bars on left relatively more important than those on right. Separates the vital few from the trivial many, Pareto principle. In our example, the first bar contributes with 66% of the overall complaints, while the first 3 bars are contributing with 82%. Steps to construct a Pareto charts. Step 1. Record the data. Step 2. Order the data. Step 3. Label the vertical axis. Step 4. Label the horizontal axis. Step 5. Plot the bars. Step 6. Add up the counts. Step 7. Add a cumulative line. Step 8. Add title, legend, and date. Step 9. Analyze the diagram. Now, we will perform an example from the manufacture of integrated circuit boards. The major defects which have been identified during the manufacture, for a given period, were given in the following table. We will follow the next steps. First, total the data on effect of each contributor, and sum these to determine the grand total. Then reorder the contributors from the largest to the smallest. Calculate the percentage of each contributor. The total of percentages should be 100. Determine the cumulative percent of total. For example, the cumulative percent of total through the second contributor is the sum of the effects of the first 2 in the rank ordering. This sum will be divided by the grand total and multiplied by 100. In order to construct the Pareto chart, we will use Insert Chart in Excel, then choose the Combo Chart to insert 2 y-axis. Use clustered column for the frequency and line for the cumulative percent. Then press OK. We can notice that more than 80% of the major defects are coming from the first 3 contributors. And this is the target from the Pareto chart, is to help us determine which categories will yield the biggest gains if addressed. To access Pareto chart in Sigma Excel, click Measure. Then click Measure Templates and Calculators, then click Pareto chart. In the template, fill in the causes and frequency. Then click Pareto chart in order to create the Pareto chart. To access Pareto chart in Menu tab, click Stat, then Quality Tools, then click Pareto chart. A new window with the title Pareto chart pops up. Select Causes into the Defects or Attribute Data in box. Select Frequency into the box Frequency and click OK. The Pareto chart will open in a new window. An inspector for a clothing manufacturer investigates sources of clothing defects to prioritize improvement projects. The inspector tracks the number and type of defects in the process. Use Pareto charts to decide the most high-impact complaints on the quality. Please pause the lecture and perform the exercise. 1. Sort the categories amount in ascending order, sum up the total. 2. Calculate percent of each category. 3. Calculate the cumulative percent. Perform the Pareto chart. It's important to know how to create a Pareto chart, but understanding what the chart is showing and being able to communicate that among team members is what makes this chart useful. In this exercise, 45.2% of the defects are missing buttons, and 23.3% are stitching errors. The cumulative percentage for missing buttons and stitching errors is 68.5%. Thus, the largest improvement to the entire clothing process might be achieved by solving the missing button and stitching problems. In the shown Pareto chart, only categories A and B account for almost 80% of the causes. This pattern shows that just a few categories of the problem account for the most occurrences or impact. Focus your improvement efforts on those categories. In the shown Pareto chart, though some bars are taller than others, it takes a lot of categories to account for approximately 80% of the count or impact. This pattern shows that no cause you've identified is more important than any other. The most frequent problems may not have the biggest impact in terms of quality, time, or costs. When possible, construct two Pareto charts on a set of data, one that uses count or frequency data, and another that looks at impact, time required to fix the problem, value impact, etc. You may end up targeting both the most frequent problems and the ones with the biggest impact. What category to consider is a very important question. In the following example, Category A errors happen a lot, but don't take long to fix. While Category D errors are rare, but very expensive in terms of time. While, in this example, Category missing button happens a lot but very cheap. Misaligned fabric errors are rare, but very expensive in terms of cost. For a problem of employee absenteeism in a manufacturing facility, there are 12 different categories, distributed among 3 main categories: lack of commitment, poor working conditions, honest excuses. So, you should use Pareto charts analysis to determine which categories will yield the biggest gains if addressed, and which are only minor contributors to the problem. Please perform the activity and send the output by email for assessment. Please download from the resources the instructional video for Pareto chart using Excel templates, Sigma Excel in Menu tab, Measure Phase Sigma Excel.mp4, Pareto chart Mini tab.mp4, Measure Phase templates.mp4. Thank you, and see you in the next lecture of the Measure Phase.